Okay, so our next speaker is Sreejith Sudhakaran from Qualcomm Technologies International Limited, where he's an engineer and senior staff manager. He's currently leading digital design and verification of IP and SOCs in Qualcomm Technologies International Limited in Cambridge. He's a proud graduate of the University of Essex and has more than 20 years of domain experience in design and verification of SOCs, from strategy, architecture, planning, execution, and sign-off. His area of expertise includes system architecture, System C-based design, low-power simulations, gate level, PG gate level, and formal verification. And the title of his talk is Challenges and Opportunities in System C and HLS-based functional verification.
Yeah, thanks, Mike. Today we are going to cover some of our experience using SystemC and HLS in one of our latest projects. So I will cover an overview of what HLS is all about, and a typical HLS flow, and how we can actually integrate the SystemC model in the test bench. I will also cover a case study results where we saw what are the benefits, what are the disadvantages with this approach. Okay, as the previous speakers already discussed about, okay, so the challenges are exactly the same. Like, we have complexity of the designs are increasing exponentially, as well as the timescales are reducing. So that remains the same. So this is a typical flow for SystemC and HLS. We can actually model the design using SystemC, and then we can take it to the high-level synthesis tool, which will actually give a very low RTL. So then again, it goes through the normal RTL synthesis and placement route. So with this approach, we can actually see that it is reducing overall test bench development time, and the one of the main advantage, right? Okay, so we have the customer requirements keep on changing, so we are able to incorporate some of the late customer requirements into the design using this flow. So this slide gives a quick overview of like typical HLS flow. So on the left-hand side, we have the SystemC based design, and we take it to the HLS tools, and then we get a RTL code related to that SystemC design. So the advantage here is, okay, so we can do the early system validation using SystemC. So it can be a SystemC test bench. It does not need to be a UVM test bench. We can also use a UVM test bench there, or it can be a MATLAB. So that way we can actually do most of the algorithm development in SystemC. So the advantage here is we can actually use the same test bench for doing the RTL verification on the right-hand side. So of course there is a kind of optimization we wanted to do here. So the tools basically give what we are asking for. Like, okay, what is the optimization we wanted to do there? Whether it is, okay, am I optimizing my design for power, area, or latency? Based on that, we can actually we can optimize the. So there are a couple of iterations we wanted to do to get to the best outcome we wanted. Okay, quickly on to test bench implementation. So the color coding, so the gray area gives handwritten RTL, and then the blue area gives the system tool generated RTL. So the advantage with using SystemC, it is actually separating your clock boundaries with the actual algorithm. You don't worry about where the registers are sitting or where the memories are sitting. So we, independent of that, right, we can actually do our the algorithm development separately. And then, of course, the gray box around it is actually the handwritten. Okay, we will be connecting the clock registers into the design to complete the functionality. So most of the HLS tools actually gives a system wrapper, which is actually shown on the blue box on the bottom. So this can be directly plug and play into the test bench. So that means whatever generated RTL can be verified using the SystemC model, which is also coming from the tool itself. We can very easily integrate it, and then we can get the data checking happening. So the next slide, again, this just gives a bit more elaborated view of what is actually happening there. So we can actually give the same input into the design, like it can be clock reset or any control signals which can go into the design. So we just need to feed the same input to the test bench. So because of the tools, the tool is actually helping us with some of the wrappers available, so we can easily integrate that and then connect the same inputs into the design as well as our reference model. So output, we can actually check the output using a simple scoreboard in that case. Like, okay, we will get a one-to-one mapping between the output generated from the reference model as well as the design output. So in this level, right, most of the time we may not find many issues, but these days the HLS tools are quite matured. So it will generate a one-to-one mapping, like whatever SystemC model we are actually giving. There are various, even before coming into a UVM-based verification, there are other formal methods to make sure these equivalence checks are actually complete. But whereas there are few cases where we may make a particular SystemC intention and then the RTL might not be exactly matching. There are few cases where this approach also will help. But the main advantage with this design, what we saw is when we do the end-to-end verification. So we may have similar algorithms. So for example, the DUT block you are seeing here, we may have different such algorithms being developed, but to club it together to generate the entire system. So that's where, right, the actual value add happening. I just wanted to give you some, it's actually a busy slide, but I wanted to get a feel of what are the results we were actually getting. So in this case, okay, so we have taken a typical generic filter design, but it is a much more complex filter design, but for the time being. So what we compared is, okay, we actually changed the parameters, which is actually shown in the table below. So we changed the processing clock. We have, okay, the tool offers few options, like we can actually do some optimization. So the tool also helps there with power gating. So it also actually tells that, okay, whether you need any automatic clock gating being inserted or not, the tool helps with that. So the last one is quite important. So we can also tell the tool like what type of latency you need. For example, okay, so you give a particular algorithm, you need to finish that in one cycle. So that will take more of the hardware. But if you are relaxed on your latency, so the tool is intelligent enough to optimize the hardware. So when I say optimize the hardware, say for example, if there is a multiplexer, it can actually reuse the multiplexer rather than instantiating it multiple times. So those are the parameters we change. And then the graph actually shows a typical comparison with handwritten RTL, which is handwritten RTL for a typical use case, along with these many variants. So if you can look at it, right, so it's actually when you go from left to right, the amount of hardware is actually getting reduced based on, okay, so based on the number of based on the latency changes. Say if you're telling 4-cycle latency, the amount of hardware is being reduced. So there are few cases where the power is quite high, but that's where the power optimization from the tool is actually helping there. So to give a summary, so it's all about, so assume that you are trying these many options using handwritten RTL. That's almost will be a time consuming process. But with the help of HLS flows, we can actually do that in really like couple of hours or 2-3 hours. We can get all those results, and then we can actually choose, okay, this is the one we really needed, and we can continue from there. That's the real advantage here. Moving on. Okay, quickly. Okay, what went well and what didn't go well. So yeah, the advantage, as I mentioned originally, so it is actually separating the algorithm versus, okay, whether there is no clock boundaries or register space or memory management. They are actually separating from the algorithm design. So that makes it quite faster. Of course, it is helping with the design verification cycle as well, because most of the things are done in the before the RTL is being generated. So most of the HLS tools, right, they gave that out of the box reference model, which we can directly integrate it into the DV. So that's also helping. So as I have shown in the previous diagrams, the integration is quite simple. We have a one-to-one mapping between the design inputs and the output. So it's a straightforward plug and play. So based on the previous slide, okay, we get an early indication of how the design is trending, like whether we are optimizing for power or, okay, what are the areas we want to look at it. That's also is an added advantage here. Okay, so areas didn't work for us at least. So yeah, so the tool generated RTL is not quite friendly. So we are not able to understand it quite well, but these days the tools are still improving. I can see that the tools are actually mapping the C code versus the RTL, which is being generated, which is actually giving quite a bit of mapping. But yeah, but that's an area still. So because of this, the coverage closure, when it comes to the coverage closure, it is actually really a difficult challenge. So one another area we were struggling is when, okay, for a single clock domain design, this approach works out of the box straight away. There is no issue. But when it comes to clock domain crossing, right, there are like 2-3 clocks involved. It is going for a toss. It is going for a toss in the sense like, so we cannot predict when the edges are coming and when do the data will be aligning. But this is where we actually need to do a bit more than bit matching. We will be doing we wanted to do some end-to-end additional checks, like for example, SNR or SINAT, something like that. So we wanted to do some more end-to-end checks to make sure even though the data is not aligned, we still get the expected performance. So the third one, okay, so there will be additional pipeline delays. As I mentioned, right, the SystemC model is only a functional abstract of it. So depending on the number of pipeline stages we are choosing, the RTL will be slightly different. So that may need a bit of tuning in the initial stages of DV. So that was also another challenge, but that's a very trivial one. I don't think it took too much of effort. So the last one, as in the previous slide, as I mentioned, right? So we were doing multiple iterations of synthesis, power optimization, just to see which is the best one is actually fitting us. So in summary, okay, so I just listed down. I don't think there is nothing new here. So the advantages are, okay, so there is definitely a quick turnaround time for the design which we are intended. And it makes the things quite easier. The number of bugs in these kind of designs, right, were considerably less compared to the RTL coded design. Of course, reducing the time to market, then it is actually helping us to absorb some of the late requirement changes. And as you have seen in one of the slides with the performance results, so it is quite good. The tool is also giving quite good results compared to a handwritten RTL. So the cons to summarize, okay, CDCs as well as it need multiple iterations to get to the best outcome. I think that's all.
Brilliant.
Thank you very much.
Thank you very much. Very dark. You get to your previous slide, though. You get a bit of backlight from that. Yes. So, how did you overcome clock domain crossing issues whilst using our HLS flow? Is there any other questions from the audience, by the way? Sorry, yeah. Let's go to that question first, and then we'll go to the clock domain crossing question.
Hi, sorry. I just wanted to ask whether your sort of experiments were successful. Are you? Is this something you're continuing with, having sort of got good results?
Yeah, definitely. Yeah, we are continuing with this approach for some of our designs as well. Yeah, correct.
Okay, so I guess it was a success. Yeah, how did you overcome clock domain crossing issues in HLS?
Yeah, thanks. Yeah. So as I mentioned briefly, okay, so clock domain crossing is a challenge in the HLS based design. So I briefly covered that. We also doing other end-to-end checks like SNR or SNDR checks. Also, we are trying to model these clock domain crossing in the SystemC as well, but we are not really successful about. Maybe I would like to open that question to the and see whether else have similar experience.
I'm not sure. I'm not sure how many people use HLS. That might be the issue.
Yeah, maybe that's the question. How many people use HLS?
You're asking for a niche of a niche, I think. So, does anybody use clock domain crossing? No, HLS. Sorry, HLS. Yeah, there's a few using HLS. Any clock domain crossing issues?
I was just wondering if you'd explored any use of formal tools to prove C to RTL or indeed RTL to RTL as you iterate.
Yeah, in fact, we are already using that for the conversion stage, right? We are already using the formal method to make sure the conversion is correct. Yeah, so the I was mentioning is top of that. Like we will have multiple systems together, so we want end-to-end checks.
Thank you.
My own experience with HLS was it was good for data path and not so good for control. Is that still true?
Yeah, that's correct. Yeah.
Okay.
So mostly for algorithms and data paths.
Yeah. Oh, Andy, there's a flood of them now.
It's not really HLS related, but when you use something like Verilator, which has a similar constraint, and you only have one clock, if you use ratioed synchronous clocks instead of CDCs, you do actually get an accurate match across them.
That's correct. Yeah, that's correct. Yeah, you're absolutely right. But in our case, right, this was actually two different clocks from different sources. Actually, you're absolutely right. Yeah.
Right. Okay. Thank you very much.
Okay.
And
Thank you.
thank you for the questions.